So here we are with start of the Calculus 2 playlist, Calculus 2 course. And so this should be fun. We're going to get into a lot of different types of integration. Integration, as you probably have seen a little bit in Calculus 1, can get a little bit more involved, although what we did in Calculus 1 probably is not too involved compared to what we're going to get into. And then once we get through the integration chapters, first half of this course, we will get into sequences and infinite series. And then we'll get into a couple other things towards the end, kind of miscellaneous topics. But it's definitely going to be interesting. It'll be challenging. And as we go through the course, you need to make sure that you're practicing as much as you can. The more you see of these, especially with the integration, but also with sequences and series as well, the more you see of these, the more familiar they are, the easier they will be. And I've said this in most of the math classes that I've taught. You want to get to where you can look at a problem and know how to start it. Especially, when you're in a structured class like this, most of the problems that you see, if not all the problems that you see on the test, you will have seen before if you've been doing the homework and paying attention. So it's not, nothing should be too surprising once you get to the test. And the way you get there is by practicing a lot. And so one thing that you will find as we go through the integration, with derivatives, it was mostly just you kind of memorize the formula, you memorize the product rule, you memorize the quotient rule, you memorize the chain rule, you memorize what the derivative of different types of functions are, such as e to the x or ln of x or the trig functions. And then you just kind of apply the different formulas that you need, and then you go from there. With integration, it's a little bit different. It can be a little bit more involved. And it's not as easy as necessarily just being able to look at it and figure it out. If you haven't already seen the type of function that you're working with. So we'll try to do a lot of examples in these videos, so that you can see kind of an array of different examples. And the more examples you see, again, the easier it will be if you see something that you haven't seen exactly that before. But you're gonna have different tools in your belt, and the more of those that you have mastered, the easier these will be. So it takes practice, and it's going to take time. So that's a big thing. So let's get started. So we're starting with what's called the substitution rule, and this may have been covered in the Calc 1 class. I think sometimes when I teach Calc 1, we get to this, and this is about where we stop. So you may have seen this before. If you have, great. If you haven't, that's okay too. One thing I will say is you might want to brush up on your basic integration. So for instance, we're seeing x cubed here. You want to know how to integrate x cubed. You want to know how to integrate cosine. You want to know how to integrate. So know how to integrate the basic functions. You probably need that as a little bit of background before we get too far into this. So what's going on with substitution? I'll let you read. You can read that rule on your own. What's going on with substitution is, if we look at this first example, we have two functions here that are multiplied together. So x cubed and then cosine of x to the fourth plus 2. And with a derivative, if you were taking the derivative of this, that would be very easy. You'd use the product rule. You would use the quotient rule, or not the quotient rule, you'd use the chain rule on the cosine part, and it'd be very easy. But with the integration, we don't have a such thing as a chain rule, and we don't have a such thing as a quotient rule or a product rule. So we have to learn different techniques. And so the different techniques, the first technique we're learning is called the substitution rule. And so what we're going to do is we're going to make this be a little bit easier to work with. So we're going to pick one of these, or part of one of these, and we're going to let u equal, in this case, we're going to let it equal x to the fourth plus 2. Now, why did we pick that? Well, you want to pick something that is, it's a little bit hard. I mean, I guess you could say a little bit of an in-between part of the function, so not too complicated, not too simple. One thing I notice when I look at this is we have the x cubed and we have the x to the fourth plus 2. Now, you don't want to pick for your u, you don't want to pick a composite function. You want to pick something usually that's fairly basic. Now, the reason we pick x to the fourth plus 2, this next part that we're going to do, we're going to let du, so we're going to take the derivative of this. So the derivative of u equals 4x cubed, and then, of course, the derivative of 2 is 0, dx. So we're taking the derivative of this with respect to x, and then this side, the derivative of u, is just du. So now, what do we notice? We have x cubed dx, we have x cubed dx. So let's substitute, or let's solve this little equation here for x cubed dx. We're going to divide both sides by 4. So we have du over 4 equals x cubed dx. So now we have this is our u, and then what's left, we have x cubed dx, and that's du over 4. So let's make substitutions. So we have the integral. We have cosine of u times du over 4. And so now what do we notice? Let's see if we can use some different colors here to kind of make sure everything is mapped into the right places. So we have x to the fourth plus 2. That becomes u. And then we have let's try green. All right, green. All right. Then we have x cubed dx. So we're going to treat that as if it's 1. And that is going to become du over 4 because of this. So we're kind of matching this up, and as course cosine is staying as cosine. Okay, so now let's go back to color here. So now we can integrate, and if you like, you can rewrite this as 1/4 cosine u du. And so in calculus 1, you could have integrated this. And so the antiderivative of cosine is just going to be sine. So we have 1/4 sine u plus c. And so now we're just going to substitute back. So what is u? U is x to the fourth plus 2. So this is 1/4 sine x to the fourth plus 2 plus c. All right, so, and then that's our final answer. So now, how do you know, the trickiest part of this is how do you know what to make u equal? And that is, once you get that, usually it's pretty easy. There might be a couple of other things that we need to do depending on the problem, but usually it's pretty easy after that. And so what you're kind of looking for when you see a function and we have to use substitution, are there two parts to this where one looks like it's kind of the derivative of the other? So when you see this, you know x to the fourth has a derivative 4x cubed. So we got the x cubed here, and the coefficients in front of that don't really matter. So if we're considering x to the fourth, the derivative of that, we get 4x cubed, right? The 4 doesn't really hurt us or help us. We can throw in constants. What we cannot do is throw in variables. We can't throw in other functions. You can throw in constants, but you cannot throw in other functions. So what I mean by that is we have this x to the x cubed dx, and we have x cubed dx, okay? If we had an x to the fourth, or if we had an ln, we couldn't do anything with, like, we can't just throw in an ln in here. We have the 4, so we can add the 4 over when we do the substitution. Okay, so just kind of things to keep in mind. We're going to look at 9 examples altogether in this section, so we're going to look at quite a few. All right, so this one, evaluate this integral. So we really don't have much to work with in terms of a substitution. We really only have the 2x plus 1. And most of the time, maybe all the time, when you are doing a substitution, you're going to pick everything that is connected with, so like you wouldn't just pick 2x. You need to pick 2x plus 1. So you're not just going to pick part of that, you're going to pick the whole thing. So let's let u equal 2x plus 1, because that's really all we have. If we let u equal square root of 2x plus 1, you can try that and then see what happens, and you can see that you'll end up with a big mess, and it doesn't really help you. So now we take the derivative, 2 dx, and now let's do the substitution. So we only have the dx. So when you get to this derivative part, look at what you have here. Look at what you still have over here minus your u. And so we have dx. We don't have anything else. And so we need to solve this for dx. So let's divide by 2, and we get du over 2 is dx. So now let's make our substitution. So we have the integral. We didn't do anything with the square root, but what's under the square root? 2x plus 1, so that's going to be the square root of u. And then dx is du over 2. Now, obviously this isn't the best way to write this, but I think when you're first starting this and learning, it's okay to write it in kind of a messy way and then clean it up. But we want to make the connection between what part is going with what substitution. All right, so the square root of 2x plus 1 becomes the square root of u, and then dx becomes du over 2. Okay, so now we'll rewrite this in a nicer way. So 1/2 square root u du. Now we need to integrate this, and this is just a basic power rule at this point. I usually like to write the square root as with an exponent. So now remember, we add 1 to the exponent and then divide by the new exponent. So we have 1/2 u, add 1. So we have 3/2 over the new exponent, which is 3/2, plus c. All right, 1/2 divided by 3/2 is 1/3, u to the 3/2 plus c. And now let's substitute back. So when you get your final answer, you don't want u in the final answer. You want, 1/3. You want your original variable. So 2x plus 1 to the 3/2 plus c. Now, the good part of this course, and this integration part at least, you can almost always check your answers. So all you got to do to check your answer is take the derivative of this and see if you end up with that. And so that makes it kind of nice. When you get to a test, you can always check your answer, and if you're close but not exact, you might be able to figure out what you need to adjust a little bit. Maybe it kind of depends there, but just something to keep in mind when you're doing these problems. You can always check your answer. All right. So we have the integral x over square root 1 minus 4x squared. All right, so we look and we have x and we have 1 minus 4x squared. So notice we're not really paying attention. So again, square root of 1 minus 4x squared, that is a composite function. We have square root of x, and then we're inputting 1 minus 4x squared into that. And so usually when you do the substitution, so when you have an f of g of x, kind of like what we have, so square root of g of x, where g of x is 1 minus 4x squared. So this is just basic composition of functions. When you have the composition of functions, this is probably going to be what you're using for u. It's at least a good idea to try it. Now, how do you know if it works? Well, it works if you end up with something you can use to get rid of whatever's left. So in this case, we have x dx. When we take the derivative of 1 minus 4x squared, we have negative 8x dx. So here is what we need. And so let's just divide by negative 8. So we get negative du over 8 equals x dx. All right, so now let's do our substitution. So we'll bring this down here. And so we have the integral. Now on the bottom, we are going to have the square root of u. And x dx becomes negative du over 8. So let's just put negative du over 8. And if we like, we can write this with exponents. So negative 1/8 u to the negative 1/2 du. Let's integrate. We'll add 1 to the exponents. We have negative 1/8 u to the 1/2 over the new exponent of 1/2 plus c. Negative 1/8 divided by 1/2 is negative 1/4. Let's go ahead and substitute. Square root of 1 minus 4x squared plus c. There we go. Okay, so maybe the first time you watch this video, it can be a little bit. Maybe I'm going fast. Maybe I'm not. Maybe it's just a little bit confusing. So watch through this video, work these out, and then maybe try to work them out again on your own. And maybe just watch a couple and then pause the video and then go back and work those couple again. And so don't try to just watch this once, and especially don't just watch me. For sure you need to be working these out with me, writing down all the steps. If I say anything that seems noteworthy that you should write that down as well. But don't just be passively watching these. It's probably not going to help too much. All right, so next one, integral of e to the 5x dx. And again, so this is again like a composite function. We could call this e to the t and then let t equal 5x, or g of t, e to the g of t, or however you want to think about it. But this is a composite function, e to the x, and then we're plugging in another function in for the exponent instead of just basic e to the x. All right. So again, the input of the composite function is, or whatever is making this not a basic e to the x, is probably going to be u. So u equals 5x, du is 5 dx. We only have the dx, so we need to divide this by 5. So we get du over 5 equals dx. Make our substitution. Integral. And we just have e to the u over 5 du. So there's our du over 5, which is the dx. E to the x is u, so it's e to the u over 5. And then, of course, the antiderivative of e to the u is just e to the u. The 1/5 is a constant, doesn't change anything. So this is just e to the u over 5 plus c. And then we'll make our substitution back. U is 5x, so this is e to the 5x over 5 plus c. All right. Moving along. All right, so now this one's a little bit interesting, and I'm not sure why this is written this way, but we'll write it like this. We'll put this x to the 5th, because x to the 5th is not under the root. Okay, so let's do this. So now, so what do we have? We have x to the 5th that could be u. We have 1 plus x squared that could be u. Now, you could try u equals x to the 5th. You find du is 5x to the 4th, but we don't have an x to the 4th. So let me just write down what I'm saying here. So is it this? So you can try these and see what happens. Okay, so then we let this part be u. 1 plus x squared which is kind of a problem because we don't have a square root here. And so how would we get the dx that's not under the square root with this thing that is under the square root? So that kind of presents a problem. We also have x to the fourth here, but we only have an x squared left over. So that doesn't really work too well. So this doesn't work. So one thing I don't want you to be afraid of is I want you to be able to be confident enough to try something for you and see if it works. And if it doesn't work, then try something else. So we tried x to the fifth. That doesn't work. Let's try 1 plus x squared. Well, we get du equals 2x dx. And so now we have something interesting. We have an x here, we have x dx, but we have x to the fifth dx that's left over. So how are we going to do this? So now this is where sometimes you need to do a little bit extra. So let's look at this. We have u equals 1 plus x squared. So what if we solve this for x squared? We have x squared equals u minus 1 of them. And so what we're doing, let's write x to the fifth. X to the fifth we could write as x times x to the fourth, right? These are the same. So let's rewrite x to the fifth as x times x to the fourth. So x times x to the fourth, square root 1 plus x squared dx. Now, we don't have an x to the fourth, we have an x squared, but how could we rewrite x to the fourth? Let's rewrite that as x squared squared. So let's keep going with this. So x times x squared squared, square root 1 plus x squared dx. Okay, so now we have x dx. We have x dx. We know what x squared equals. It's u minus 1, and we have x squared right there. And then we have 1 plus x squared. That one equals u. So now it looks like we have everything taken care of. We need to divide this by 2 to get the x dx by itself. All right, so now let's make our substitution. So x dx is du over 2. Maybe we'll do some colors in this one. So let's do a red. All right, so we're going to do red is going to be du over 2. Let's do green. Is going to be x squared. So x squared is u minus 1. So this x squared is going to be u minus 1 squared. And then we'll just do our original light blue as square root of 1 plus u squared. So that would be the square root of u. All right. So now one thing you might remember from Calculus 1, we have a 1/2 here. We can pull that out. So let's just pull that out. 1/2, and we'll kind of write this a little bit nicely. Okay, so now this looks a little bit tricky maybe, but we can work with this. So we can FOIL this out, multiply that out. 1/2, we'll just go ahead, we'll write square root of u up here. U minus 1 squared is u squared minus 2u plus 1. Let's distribute the square root of u. All right, so u to the 1/2 times u squared, that's going to be u to the 5/2. Square root of u, or u to the 1/2 times negative 2u, that'll be minus 2 to the u 3, 2 times u to the 3/2. And then plus u to the 1/2, square root of u times 1. All right, so now let's integrate this, and we'll worry about the 1/2 later. So add 1 to the exponent, divide by the new exponent. So that gives us 2/7 u to the 7/2. 5/2, 2 divided by 5/2 is 4/5. Plus 1/2, so 3/2, that'd be 2/3 u to the 3/2 plus c. And then we can go over here and substitute 1 plus x squared in for all of these u's. So, and we can distribute the 1/2. So 1/2 times 2/7, that's going to be 1/7. 1 plus x squared to the 7/2. 1/2 times 4/5, so that is 2/5. 1 plus x squared to the 5/2. And then 1/2 times 2/3 is 1/3. 1 plus x squared to the 3/2 plus c. And then that is our final answer. Okay, so that one was a little bit tricky. So what did we do? We made a substitution. U equals 1 plus x squared. We took the derivative of the substitution as we always do. Now this part is kind of the new part because we had something left over. So we found our x in our dx, which goes there. We found our square root of u, which goes there, but then we had this x to the 4th left over. And when you have something left over, a lot of times you would just need to solve this for x or x squared, whatever is most convenient. We didn't need to solve for x because we have an x to the 4th. But if this was an extra x, then we would take the square root of the u minus 1. But you do this whenever you have something left over after making your substitutions and seeing that something is still there that you need to take care of. So whenever you're doing substitutions, you got to make sure that everything is taken care of. So all the variables, all the expressions are written in terms of, or can be written in terms of u, and you don't have any x's left over. All right, so let's do one more, and then we'll stop this one and do definite integrals on the next one. Okay, so tangent of x. Now this is an integral that you could memorize. I mean, just like you memorize the integral of sine or the integral of cosine or e to the x or whatever. So we're basically going to derive this formula. Now, tangent of x is sine of x over cosine of x. And so now, what is our substitution? So I guess we could do sine of x. We might be able to do cosine of x. And so let's do the wrong one. I'll show you the wrong one first, because if we let u equal sine of x, so question, is this going to work? And the answer is no. Du equals cosine x dx. Well, now how are you going to get, so we don't have cosine x dx, we have dx over cosine of x. So these are not on the same side of the fraction. But here they are. So that doesn't work. So we can't really do anything with that. If you divide by cosine of x, you end up with du over cosine of x. That doesn't work. You don't want x's over here anyway. So this doesn't work. So the right way to do it is to let u equal cosine x. And that's the only other thing to try. Then du is negative sine x dx. And so now we can divide by -1 if you like. So negative du equals sine x dx, which is what we have. And then, so this becomes sine x dx is negative du over cosine x is u. All right, so now this becomes negative ln absolute value cosine. Well, let's do u. I was going to substitute back too soon. Ln of u plus c. So that is negative ln of cosine x plus c. Now, that would probably work, but typically you don't see the integral of tangent x written as negative ln cosine x. So you could actually write this as, so we could do this. Ln of 1 is just 0, so this isn't changing anything. 0 minus that, which we have that up here. We just don't need to write the 0. All right, so now use your log properties. Ln of 1 over cosine x. And what is 1 over cosine x? That is secant x. So this is typically the way you write the antiderivative or the integral of tangent x. You write it as ln of secant x. Of course, negative ln of cosine x is the same as ln of secant x. So typically we write it this way, not with cosine. Okay, so we'll stop this one here, and we'll pick up on the next one. We'll do a few examples with definite integrals. It's kind of the same thing, but you can shortcut a little bit as far as the substitution goes with those. So we'll see how to do that in the next one.